We're going live. We are live. So hello, everyone, and welcome back to the Latin American Webinars on Physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. This is webinar number 176, and we're having Claudio Toni as a speaker. Claudio carried out his PhD at La Sapienza in Rome, Italy, which was followed by a postdoc at Padova, also in Italy. He then moved on to the LAPTh laboratory of the CNRS in France, where he is currently a postdoc. Today, Claudio will give us an update on the Atomki anomaly and its interpretation in terms of the X17 particle. Before we begin, let me remind, as usual, that you can ask questions and make comments via the YouTube live chat system, and all of these questions and comments will be passed on to Claudio at the end of the talk. Okay, so Claudio, we're all yours. Thanks very much for having me here.
Thanks. Hi all. Thanks for this opportunity. Now, can you see my slides, right?
Everything good.
Okay, let me try. Okay, all good. So, okay, as Joel said, this talk will be about the Atomki anomalies and the X17. And during this presentation, we explain you what Atomki is, what are these anomalies, and what is the X17. So let's start saying that so far we are stuck with the standard model field content. So we already know the quarks, the leptons, the gauge boson, the Higgs boson, discovered just 15 years ago. But now we had no idea how to move on and go beyond the standard model. But apparently now, 90 years ago, paper came out from the Hungarian collaboration named Atomki, who claimed to have observed some experimental anomalies in nuclear physics, which are due to a new particle, to a new state, not contained in the standard model, which they called X17, and they proposed these anomalies as the first signal of a new beyond the standard model particle called X17 with a mass around 17 MeV, that's why its name, which will be a neutral boson with an unknown spin and unknown dynamics and couplings to all the other particles in the standard model. So the structure of my talk is made in a chronological way. So we start showing you the Atomki search anomalies performed between 9 years ago and until a few years ago. Then I will introduce you to this hypothesis for new particle interpretation of the anomalies, the particle called X17. Then I will first talk about the first work I did on this subject. Then I will show you new experimental days that just came out a few months ago in the end of 2024. And then I will talk later about a theoretical update I did after the few experimental dates came out. And I will conclude just by showing you what are the upcoming searches that we should be expected in a few weeks, actually. Now, first argument will be what is Atomki, what is search, and what are these anomalies they found out. So, Atomki is a Hungarian collaboration who works on nuclear physics, and the idea behind their search is that if you take rare nuclear processes as nuclear transition, where nuclear transition means that an excited nuclear state decays into the ground state of the same nucleus while emitting a particle, like for example in QED we have the real photon emission, which is a first order in QED coupling process, or otherwise we have the emission of electron-positron pair, which happens through the emission of virtual photon, which is a process at the second order in the QED couplings. Now, the idea of the Atomki was if there is a massive unknown particle which is emitted during this nuclear transition and then decays in the place minus, this will be a process at the first order in nuclear physics coupling compared to its background, which will be given by the internal pair creation in QAD, which is at the second order in QAD coupling. So the idea was new physics, new particle states with a MeV mass can be produced in these nuclear processes, and it will be possible to see them over the background, even if they are weakly coupled. Also, there is this nice feature that the QAD distribution of the E plus E minus pair over the depending on the angle between the two leptons actually peaks at small angles and then have a tail at larger angles. While a process where a massive state is emitted and it then decays to E plus E minus have a different structure due to the kinematics of the process. In this case, new physics will appear through a bump-like distribution peaked at large angles. This means that if you see those few examples of QAD distribution of the internal angle between the E plus E minus pair, the idea of Atomki is that during the research, they should be observed if such particle exist. They should be observed a bump over this tail. And surprisingly, they observed such bump in 2016. They measure the decay of an excited state of beryllium-8, and they observe that while, as you can see, the background, most of the points follow the background QAD prediction. There are a few points around 140 degrees where we observe an excess of events, which is above the QAD prediction, with a statistical significance of 7 sigma. Which means that this excess is not just a statistical fluctuance, it has a real physical meaning according to the collaboration. And they claim that this anomaly actually can be well fitted by assuming that there is a new contribution due to a particle emitted in the nuclear transition and then decaying into E plus E minus pairs, and is well fitted with a state of mass around 70 MeV. After this anomaly, the collaboration decided to test this kind of new physics signal also in different nuclei, because in principle it can be observed in different nuclei. They first studied beryllium. 3 years later, they studied helium, and again, surprisingly, they observed a similar peak in their measurements. And they observed this peak and a slightly different value of the internal angle, where now the peak of events is around 110 degrees. And again, this excess has a nice statistical significance, which means, again, it's not a fact of fluctuation of statistics. There is apparently something going on which cannot be explained only by standard model, which means only by QAD processes. And again, after helium, they decided to test these anomalies, this signal, also with another type of nucleus, and they studied carbon transition. And again, they observed different energy of the processes, an excess of events, which again, according to them analysis, can be well fitted by a particle emitted in a transition decaying to E plus E minus with a mass around 70 MeV. So, of course, first of all, before claiming about new physics, we need to calm down and ask, what if these anomalies are due to some unknown, unexplained, but still effect within the standard model, where there have been, of course, some studies on it. First, after the first result in the beryllium experiment, there was a paper by Zhang and Miller, where they provide a better prediction for the background from QED, and they also they also test the hypothesis that these anomalies are not due to some BSM state, but they are just due to some unknown dynamics in nuclear physics, which could be, in principle, parameterized by a form factor. They show that this parameterization with an unknown form factor actually could fit the data, but then the length scale associated to that form factor is actually larger than the one observed in the scattering experiment on beryllium nucleus. So apparently, nuclear physics is not a good explanation for these anomalies. And then years later, after the result from the collaboration in the helium experiment, an ab initio calculation of the standard model prediction was calculated for the helium transition, and they indeed checked that the peak observed in the experiment cannot be explained by the standard model, which means it cannot be explained by QED prediction, so that there is no way standard model can produce a resonance-like, bump-like structure in the angular correlation in such experiments. So, given that standard model cannot give us any explanation at the moment for this effect, we can start talking about the hypothesis of a new particle due as responsible for these anomalies. So actually, this is a scheme of the experiment made by Atomki. So there is a target of lithium hit by a proton beam. In this way, they created the excited states of the beryllium-8 nucleus, which in their experiment decays to the ground state of the same nucleus while emitting a photon or a virtual photon decay plus and minus, or as they claimed, even produce a massive real state called X, which decays then in E plus and minus. And if this is the case, we know that this particle must have a mass of 70 MeV around that value, because it's the best fit value given by the experimental measurement. This particle, since must decay into a plus and minus, is a natural boson, and since it must produce a signal in the experiment, it cannot propagate more than 1 centimeter, otherwise the E plus and minus pair will be produced outside the apparatus of the experiment. So it must be a short-lived boson. Then, since the signal rate is given by the production rate, so this particle must be emitted in a nuclear transition. This means that it for sure it's coupled to nuclear matter, and then it must decay to E plus and minus. So it must decay also to electron and positron. These are only the few certain information about this particle, but we have no idea so far which is its spin actually, which type of coupling has to nuclear matter and electron and positron. So before talking about dynamics and couplings and all the stuff, let's first start with the kinematics of the process, because I think that so far the best argument in favor of the X17 is based on simple features of the anomalies that can be naturally explained by the kinematics of the X17 of the new particle interpretation. So first of all, I show you that these anomalies appear as bump-like in the quick detail, and this anomaly appears as peaks at different value of different values of the angle between the E plus and the E minus, depending on the nucleus, so on the process, and particularly on the energy released in the nuclear transition. And these peaks actually are predicted just by the kinematics of the process. So these peaks, these values of the peaks, depends only on the mass. And as I will show in this plot, these peaks reproduce the experimental values just by assuming the same particle, all these anomalies, with a mass around 70 MeV. And actually, a recent paper from just 2 years ago, they made a fit of just the mass of the particle just by using the angular observable of the experiment, and they obtain a very good fit, obtaining a mass value of 16.85 MeV. So then moving on, the collaboration observed that this bump-like structure not only appears in the angular correlation, but it appears also, of course, in the mass invariant distribution, which is naturally because since the excess is due to this new part interpretation, this must be a peak at a mass invariant value given by the mass of the particle. And indeed, it's what they observed. And finally, a very nice feature is that in the first experiment of helium, they split the data into two parts, dividing based on the value of a parameter called energy asymmetry, which is defined, the Y parameter is defined as the difference between the positive and electron energy divided by their sum. And while for E plus E minus pair produced by QED, these two parameters, the angle between the leptons and the energy symmetry, are independent, in the pairs produced by the decay of the X17 are actually linked, and for the setup of beryllium, they must lie in the blue line I show you in the plot on the left. And as you can see, Y is fixed to be within minus 0.5 and plus 0.5. And indeed, they observed that if you split the data into two pieces where the Y is smaller in absolute value of 0.5, they observe an anomaly. They observe the excess, the full excess. While if you only observe the data, the pairs with a Y parameter large in absolute value of 0.5, you observe that the data will reproduce the background prediction, which is not totally trivial, this feature. And to me, all these simple observations are actually the strongest argument in favor of the new particle interpretation. And because of this, actually, I decided to work on these anomalies. And during my PhD, I made my first publication on this topic, where the topic was, okay, because of the features I showed you before, I quite convinced that X17 hypothesis is kinematically consistent in all the anomalies observed by collaboration. The question becomes, okay, but is the X17 particle dynamically consistent for all the anomalies? And if so, there is a way to tell which is the most promising spin parity assignment for this particle. So since we know quite nothing in the spin particle, we can just assuming something simple and starting with the parity conserving scenarios and limiting ourselves to spin to particle with spin 0 and 1, we have just 4 cases to study, which is a vector X17, a scalar X17, an axial vector X17, a pseudoscalar X17. And since we know nothing about this particle, we will study the dynamics under an effective field theory approach, where we write just the coupling to the nucleons in the most general, the most general couplings to the nucleus for this particle, depending on the spin parity of each scenario. But first of all, we can do a simple exercise, just like in quantum mechanics. Since nucleus and excited states of nucleus have a definite spin and parity, because QCD conserve parity, we can actually calculate it by hand the angular momentum of the particle of the X17 emitted in X transition. And we can observe that actually, because of angular momentum and parity conservation, there is no way that a scalar particle is emitted in a baryon transition due to the quantum numbers of the nuclear states. So this means that the scalar scenarios can be already excluded because it cannot explain the beryllium. And we would like to have a common explanation of all these anomalies. And for the same reason, parity conservation don't allow the pseudoscalar particle to be emitted in the carbon transition, so that we can already exclude it just by parity conservation 2 of the 4 scenarios we wanted to study. So we are left with just 2 scenarios to study, which is a vector and axial vector X17. Through some detailed calculation on the theoretical side, I won't talk about, just to be brief. Our analysis aim to match the theoretical prediction we calculated with experimental data taken from Atomki papers, and trying to understand the range, start a range for the nucleon couplings to X17, and see if those ranges are compatible among all anomalies and with the experimental constraints from other searches. And since we are assuming in this case that basically X17 is a spin-1 particle, a spin-1 particle cannot decay into photons. It can decay because of the Young theorem. It can decay to E plus and minus. And assuming for simplicity that there is no coupling to neutrinos, there is no other possible decay channel for this particle, so that it's simple to assume that the branching ratio of this particle to E plus and minus is actually 1. With that in mind, we produced this plot in 2022, where we plot for each of the anomalies the 1 and 2 sigma region where they can explain each anomalies. And we consider also the constraint coming from protophobia, so the constraint coming from the search of a natural pion decay into gamma X dark state measured by an X48, which is the black line, which gives you us where we must lie within to be compatible with the experiment. And later, after our work, Ostart and Pospelov added to this picture the constraining for spin-1 particle coming from the Sindur search, which put a bound, an upper limit on the branch ratio of the charge pion decay into E plus, neutrino, and dark state, which is this very small blue line. And as you can see, there is no way to explain all the anomalies while being within the region compatible with the syndrome and with the N64 bounds. So we ended up that the vector scenario actually is excluded. Now we move on to the axial vector scenario, and we see that the syndrome constraint is slightly, the region from the syndrome constraint is slightly larger than the vector case, and there is a way to explain the beryllium, the helium anomalies together while being compatible with all the experimental constraint. And actually, at the time we published our first work, we claim that an axial vector X17 will be also able to explain some other experimental anomalies, such as the KTV measurement of network pion to E plus E minus and the electron G minus 2 measured value. However, 1 year ago, after our work, someone calculated the theoretical prediction for the carbon case, which we weren't able to calculate at the time, using a particle share model approximation for the carbon excited state, so that they were able to connect the X17 decay rate to the gamma decay rate of the same nuclear transition. So they had the possibility to make a prediction for the X17 production rate, and they obtained that the region that could explain the carbon anomaly is in tension with the syndrome constraint. So that the only scenario we consider viable at the time of the first work I did together with Daniele Berducci actually is in tension with the experimental data, and it didn't work out. So this was the situation 2 years later, 2 years ago, actually. Then there was an update, experimental data from a different experiment from McDo, which aims to reproduce the Atomki result and perhaps confirm the Atomki anomalies. The McDo experiment, which is placed at a PSI, was actually able to remeasure the beryllium transition, and they took data during a run in 2023. And just a few months ago, they published their data, and the results showed that there was no significant signal observed in their measurement, which means that they claim that they didn't observe any anomalies actually. However, this doesn't mean that the X17 hypothesis is totally excluded, because the Mercury's collaboration claimed that their measurement agrees anyway with the Atomki result within 2 sigma. So we combine actually the Atomki and Mercury result, and we saw that actually through a simple chi-square analysis, the best fit of the two measurement actually gives a best fit value which is within 2 sigma of both the experiment. So while the Mercury result actually weakness the Atomki anomalies, at the same time, a final exclusion of them is not established. We need more data to establish a final exclusion, and instead we can combine them, obtain a combined value which is agreed with both experiments, even if only within 2 sigma for both the experiment. So given this in mind, we did actually few months ago an updated work on the subject, where again the question remains the same. Since McDowell was not able to give a final exclusion of the X17 hypothesis, we should ask again to ourselves, is the X17 dynamically consistent for all the anomalies? But since we were not able to explain the anomalies with the scenario I showed you before. So with the particle with spin 0 and 1, we choose to go a bit beyond that and talking about what a spin 2 scenario, which is a bit more exotic, but since the less exotic scenario didn't work out, we tried with a spin 2 particle. And we had in mind a scenario where there is beyond the standard model sector, which at a certain point, since a spin 2 particle cannot be fundamental, this BSM sector below certain energy, it confines like QCD, and among the spectrum of this confinement regime, there is actually a spin 2 state, and this spin 2 state, due to some EV mediator among the two sectors, the standard model and beyond standard model sector, this spin 2 particle can interact with the standard model fields. Note that in this scenario we had in mind the mass of the EV mediator, so the mass of the interaction between the standard model and BSM is different and independent from the scale of the confinement in the dark sector, which should be around 4 pi times the mass of the X17, so it should be around 200 of MeV. So first of all, as we should work again in a effective theory approach, but in this time for a spin 2 particle, a Lagrangian approach was difficult due to the fact that the physical degrees of numbers of a massive spin 2 is 5, but in a Lagrangian approach we have to introduce a tensor field, which is a total of 16 degrees of number. So there are a large number of unphysical degrees of freedom to deal with in a Lagrangian approach. So instead, we started with the on-shell amplitudes, and we went down the most general on-shell amplitude for a spin 2 particle coupled to fermion, which is a total of 4 independent coupling, CF, C tilde F, DF, and D tilde F. However, just by dimensional analysis, we can see that the DF are actually suppressed by insertion of the EV mediator mass compared to the CF coupling, CF and C tilde F couplings, so that we can assume that the two last lines of the on-shell amplitude are negligible, so that we are left with only two type of couplings, which is one refers to a spin 2 particle with a positive parity, let's say a vector tensor X17, while the other one refers to a spin 2 particle with that negative parity, so an axial tensor X17. So again, starting from this on-shell amplitude, we evaluated with the same methodology we used in the previous paper the theoretical prediction for spin 2 X17, but again we found out that there is tension between the region where we can explain Atomki anomalies and the experimental constraint. In particular, in this plots, they are shown the case of an axial tensor X17 on the left and a vector tensor X17 on the right, where on the left plot, the yellow and orange region are the region that can explain within 2 or 3 sigma all the anomalies from Atomki, while combined with the vector result. But the gray region is actually excluded by only the syndrome bound. So the axial tensor scenario actually is completely excluded by order of magnitudes by the syndrome searches. Meanwhile, we can actually explain, even at 1 sigma, all the Atomki anomalies with a tensor vector vector tensor X17, but actually the syndrome bound disfavor also these scenarios, as we must lie within this ellipse you can show on the right plot, which are the solid, the dashed, dotted dash refer to different values of the coupling to the electrons, since it is involved in the syndrome theoretical prediction. But in none of these cases, we were able to lie within this ellipse where we can actually survive the syndrome bound. So we are left that even spin 2 scenarios are out. So if I can make a brief theory recap, in all the work I did so far, I consider all the possible scenarios of parity conserving in 17 states with a spin of equal to 0, 1, and 2, so that we have a total of 6 cases to study. But none of them provides actually a viable model for the new particle interpretation, because a scalar cannot be emitted in the baryon transition, so it's excluded. Pseudoscalar as well, because they cannot be emitted in the carbon transition. While a vector cannot explain all the anomaly consistently and actually excluded by syndrome and X64. Then there is the axial vector, which after the recent theoretical update 2 years ago, there have been shown that carbon data are in tension with the syndrome constraints. And last, I show you in the previous slide that even spin 2 scenarios with definite parity are excluded because there is tension between the data, the Atomki data, and the syndrome constraint. So I would say that at this point, it makes perhaps times to study in the future parity violating states, which so far has not been done actually, and it might be a direction for future researches. And this was basically what I can tell you so far on the theoretical side. So let's just talk a brief about upcoming searches for the X17, and in particular, an interesting search is the one that can be performed, has been performed at PADME. PADME is a BIMP-like experiment where the positron BIMP are its electron, and in such experiment, PADME could resonantly produce the X17 directly. So PADME in principle cannot confirm the Atomki anomalies, but it could test the new particle interpretation itself. And there was a nice paper. There was a paper of the other collaboration in 2022 where they claim that they were able to close the spin-1 parameter space of the lepton coupling to the X17, which was nice because at the time we believed that the axial vector was the most promising scenario for the X17. However, apparently, this plot is more recent. It's like a few weeks ago, actually, where they showed that actually they were too optimistic on the paper made a few years ago, and actually they can test a large portion of the parameter space. This is just the example of the spin1 for spin1 X17, but they cannot completely test all the space between the CLO and any 64 constraint, so that they will be able to probe a large portion of the parameter space for X17, but not completely exclude the new particle interpretation. And to this regard, actually, in 2 weeks, there are going to be a workshop in the dark matter colliders in Genoa, where in one of the days of this conference, there's going to be actually a talk by me on the same topic I'm talking about now, and there is going to be a talk by the PADME experiment by the head of the collaboration, which hopefully will finally give the result of their analysis of the data they took in order to confirm or exclude the X17, the new particle interpretation Atomki anomalies at Padme. And say that this is the end of my talk. So thank you for your attention.
Great. Many thanks for the talk. It's been very illustrative. So we are now open for questions. I have a bit, but maybe the other organizers would like to start. If not, I'll go first. So the easy question is, okay, so this X17 will couple to electron-positron pairs. You did mention neutrinos, right?
Yeah.
So in principle, this thing could decay into a neutrino-antineutrino pair. So could there be any constraints coming from the neutrino sector on this particle?
Yeah, there are actually constraints on the neutrino couplings coming from neutrino scattering on nucleus. So yeah, let's say I said for simplicity we neglect those couplings, but actually there are also constraints that can be easily avoided by putting that coupling axis 0 or just suppressed. And of course, on the UV perspective, we know that since electrons are linked to the neutrino by the SU2 symmetry in the standard model, there should be actually, we should expect the coupling to neutrinos, and we should, if we manage to do a UV model, to explain why then they are suppressed compared to the electron coupling in order to avoid those couplings. But yeah, in principle, you should consider there are constraints of neutrino coupling coming from neutrino scattering nucleus.
Okay, super. Thank you. I don't know if any of the other organizers would like to make a question. If there's anything from YouTube. Okay, we have a question from YouTube from María Ángeles Pérez Garcia, saying that, hi, nice talk. Perhaps I missed it, but are there any astrophysical bounds coming from cooling supernovae?
We talked a bit about it, but as I said before, since the beginning, since this particle must give a signal in the apparatus, it cannot travel more than 1 centimeter, and it's not very relativistic. So basically, its lifetime is very short. Life is very small. It should be, if I remember correctly, smaller than 10 to the minus 8 second. So we talked a bit about astrophysics bound from cooling, for example, but this particle decay too fast to bring out energy from any astrophysical object. So far we didn't manage to put any constraint on X17 with the astrophysical object because of the very short lifetime.
Super. Thank you very much. Let's see if we'll see in a bit if there's a follow-up, because there's a bit of a time delay between one and the other. Any other questions?
Yeah, I have a question for Claudio. Claudio, in this with this anomaly indication, or let's say, is there any room for theories that are flavor dependent? Let's say that in principle, yeah, it could be coupled for electron and positron because it's what can be measured in Atomki or other stuff, but to be dependent for instance coupling to muons or lepton flavor, changing like muon electron or something like that, or this goes beyond the expectation, let's say.
First, I would say that coupling to muons would be harder to measure because the X17 can decay to E plus and minus, so that, for example, here in the signal rate, the sigma depends, the production rate depends at the first order in the coupling, while because the X17 decays is into E plus and minus, there is a branch relation factor. So we don't pay an extra new physics coupling, which is small, while because the X17 cannot decay into muons, processes with muons will require will be processes at the second order new physics couplings, and so they will be very, very suppressed. Say that at the moment we are still at the level of let's try to explain an effective field theory approach, just the Atomki anomalies, so just consider only coupling to nucleons and perhaps electrons and positrons. So far we didn't manage to do that, so couplings to muons are still beyond the actual situation.
Yeah, just to because I was thinking usually in some of the models or expectation that there is for lepton flavor changing decay, for instance, mu to E gamma, usually are done by loops. So I was thinking that maybe the X17 could be inside of one of these loops for these rare processes. Let's say, like to contribute to this kind of rare decays in other particles.
Yeah, I agree. It might be, but at the point we are, it's still too early to talk about other type of effects the X17 could have in other processes. We still haven't a viable model just to explain the Atomki anomalies by themselves.
Okay, thank you.
Right. So the only thing you need is to couple to the same particles in the generation. But the loop effects that Roberto mentioned are interesting because in principle maybe they could contribute to the G-2 of the electron. I remember that I don't know if there is anything that has been done in this direction.
Well, yeah, the X17 could contribute a one loop to the G-2 electron. In that case, but in the case it's still coupled only to electrons.
Yeah, but I don't know if there's any constraint coming from the G-2 of the electron. That there was this small anomaly some years ago, in contrast to the one of the muon, right? I don't know if
I think there's still a small anomaly in the G-2. And indeed, when we did the first paper, we claimed that the axial vector an axial vector X17 was even able to explain not only the Atomki anomalies, but with the same range of couplings, also the electron G-2 anomaly.
Okay. All right. Interesting. I don't know, any other questions from the coordinators? So in principle, yeah, I wasn't aware of this result by Meg, because initially when you have for instance, in the discovery of the Higgs, right, you have Atlas, you have CMS, right, that are two experiments with different people doing, completely different, using completely different techniques to do this measurement, so that there is no doubt on the experimental result. So the people in Atomki, I guess that they tried to do this by changing the nucleus that they were using, right? And so for me, MEG2 is okay, an initial step towards doing this kind of like Atlas versus CMS, like comparing different techniques. So my first question is if there are any other attempts at cross-checking the Atomki results using the other nucleon. And the second question is if there's when should we expect any update from MEG2 in this sense? I don't know if you're aware of that.
There have been a few more proposal of experiment to check the Atomki anomalies. One in Canada, one in the experiment called LAPTh at CERN, if I'm not wrong. But I'm not aware of any updates on the situation today for those experiments. While for MEG2, I heard that they wanted to take more data in the next run, but I'm not sure they will. I heard that was the idea since the exclusion was not final. They wanted to take more data in order to deny completely at the end at least the beryllium Atomki anomaly.
Okay. Great. So I have no more questions, and there's no other question in YouTube. So I guess we can finish here. Thank you very much, Claudio, for the talk. It's been great. I've learned a lot. Before we log off, I'd like to remind everybody that in 2 weeks' time, we have Julia Gerlein giving a talk on neutrino factories. So please stay tuned. Okay, thank you very much once again, Claudio, and we'll see you around.
Thank you.
Bye, everybody. Okay, we're offline. Okay.